concavity and the second derivative test. Alright, let's take a look at the second derivative test for critical points. So our goal of this test is to help us determine whether or not there's a local maximum, local minimum, or neither at the different critical points we find. So we're going to assume that the function is differentiable and let C be a critical point of f of x. If the second derivative exists, and if we plug the critical point C into the second derivative and get out a positive value, then f of C is a local minimum. If we plug in the critical point to the second derivative and get a negative value, then f of C is a local maximum. But if we plug in the critical point and get out 0, which is neither positive or negative, then the test is inconclusive. So f of C might be a local max, local min, or neither. So to find out which one it is, we should go back and use the first derivative test for critical points. So a lot of students get this mixed up with a lot of other things because we've learned so much at this point. So I want to show you the graphical representation of what's happening. So again, this is a test for critical points. And remember that critical points is where the derivative is 0 or undefined. So let's take a look at this left image right here. So let's say x equals 1 is a critical point, which means that at 1, the derivative is 0, so notice there's a horizontal tangent line. Now above it is the second derivative test for critical points being applied. So we know that x equals 1 is a critical point because the first derivative is 0. There's a horizontal tangent line. Now if you substitute that critical point, 1, into the second derivative and get a negative value, well, if the second derivative is negative, then the original function's concave down, or it looks like a downward facing bowl there. So if I have a horizontal tangent line and a downward facing bowl, then that means at that critical point, I must have a local maximum. So when the second derivative of the critical point is negative, I have a local maximum. And on the right side here, I have a critical point occurring at 3. So there's a horizontal tangent line on the function at 3. But substituting 3 into the second derivative gave me a positive 6, meaning that if the second derivative is positive, my function is concave up. So if I have a concave up function, and I have a place with a horizontal tangent line there, then at that value, I must have a local minimum. And then the third part of the second derivative test isn't able to be depicted on a graph because it doesn't really help us. If the second derivative at the critical point is 0, we have to try something else. Alright, so let's look at the process for using the second derivative test to analyze critical points given f of x. So the first thing we need to do is find the critical points. Now remember, critical points are ones where the first derivative, f prime of x, is 0 or undefined. And here's where students get all mixed up because they think, well, second derivative and they think inflection points. But remember, it's the second derivative test for critical points. So set the first derivative equal to 0 or undefined. Step 2 is to substitute each critical point, c, into the second derivative and then determine the sign. So if the sign of the second derivative at c is positive, f of c is a local min. If the second derivative is negative, then f of c is a local max. Alright, in this first example, determine whether each critical point of f of x equals 2x cubed plus 3x squared minus 12x plus 1 is a local minimum or a local maximum using the second derivative test. So first we need to find the critical points. So the first derivative is 6x squared plus 6x minus 12. And I'll need to find where this is 0. So if I factor out the 6, I'll be left with 6 times the quantity x squared plus x minus 2. So if I set this equal to 0, well, dividing by 6 gets rid of my 6. And this factors to x plus 2, x minus 1 equals 0. So my two critical points are negative 2 and 1. Alright, so if we were using the first derivative test to determine if these were local mins or local maxes, I would have to create my number line and my intervals and pick test points. But the second derivative test has us stop when we find the critical points and jump to finding the second derivative. So f double prime of x is 12x plus 6. So I'm taking the derivative of the first derivative. And then what we do is we substitute in our critical points into the second derivative. So f double prime of negative 2. So 12 times negative 2 plus 6. So 12 times negative 2 is going to give me negative 24 plus 6. This quantity is going to be less than 0. So what that means by the second derivative test is that since the second derivative at the critical point is negative, well, that means that I have a function that is concave down. So if I have a concave down function, that means that at negative 2, there is a local maximum. So f double prime of negative 2 is less than 0. So by the second derivative test, f of negative 2 is a local max. So now I have to see what happens when I substitute in 1. So f double prime of 1 is 12 times 1 plus 6, which is greater than 0. So the first derivative is positive, which means that at the critical point I have a function which would be concave up, so I have a local minimum. So by the second derivative test, f of 1 is a local min. So depending on how easy or difficult it is to find the second derivative, oftentimes applying the second derivative test is a little bit shorter than finding all the intervals of monotonicity and determining whether there's a change from increasing to decreasing or decreasing to increasing. This one is just a matter of substituting in values, the critical point values, into the second derivative and understanding what happens when those values come out to be positive or negative. All right, in this next example, analyze the critical points of f of x equals x to the fifth minus 5x to the fourth using the second derivative test. All right, so we need to find the critical point, so I need the first derivative, so 5x to the fourth minus 20x cubed, and I'll need to set this equal to 0. So I'm going to go ahead and factor out 5x cubed, and what I'll be left with is x minus 4. And I'm going to set this equal to 0. So in other words, 5x cubed equals 0, x minus 4 equals 0. So x equals 0 and x equals 4 are my critical points. All right, so now I'm told use the second derivative test to analyze these critical points. So I need to find the second derivative, which by the power rule is 20x cubed minus 60x squared. And what I'm going to do is write this in factored form. So I'm going to pull out a 20x squared, and I'll be left with x minus 3. And the reason for that is because I'm going to want to substitute in my critical points to determine the sign. And so the first, the unsimplified way of the second derivative being written is going to help me solve plugging in 0 pretty easily, but the second one is going to help me solve what happens when I plug in 4 a little easier. So f double prime of 0, well, if I substitute that into this top one, I'm going to have a 0 minus 0, so f double prime of 0 equals 0. So using the second derivative test, by SDT, all I have is an inconclusive result. So what I would have to do, if I needed to find exactly what was happening at this critical point, I would need to try the first derivative test. But because the instructions are telling me analyze using the second derivative test, we stop at this conclusion that inconclusive. We don't know what happens. Could be a local max, could be a local min, could be neither. So now I'm going to substitute 4, the second critical point, into the second derivative, and I'm going to choose to plug it into this factored form here. Because when I plug in 4 and square it, it's positive. And when I plug in 4 minus 3, I'm going to get 1, which is positive. So f double prime of 4, I'm actually going to erase the equal sign because all I really care about is whether this quantity is positive or negative. So f double prime of 4 is positive. So by the second derivative test, f of 4 is a local minimum. So this is the one that doesn't quite seem intuitive, right? Because we said the second derivative is positive, and then we arrived at a conclusion of minimum. So usually we think positive goes with maximum, but the second derivative is positive means that the original function is concave up. If the function is concave up, there's a local minimum at the critical point. So since f double prime of 4 is greater than 0, the second derivative test guarantees f of 4 is a local min.